Thank you.
Sure, thank you. So, okay, I'm going to start again. So, good morning, everyone. And we're going to talk about UML and object-oriented analysis and design. We're going to start with, just a little bit of introduction about why we need this, what we need, how it's going to help us, basically. And we're going to also introduce analysis and combine with how UML is going to help us during this process. And then we're going to talk about the design and again how all the information we captured during analysis and all those diagrams that we were able to draw and do the modeling based on them, how they're going to now help us to do our design, what kind of diagrams we can use an output of our design. And then at the end we're going to go with an example, so hopefully we can use all of those knowledges basically that we gain in the part 4, and so we see a real example of it as well in this part. So before I start, just like to know if anybody have any question, if you have access to the slides or any particular before I start. And also I want to know if anybody familiar before, used the UML before in any senses or any way, which tools you used if you did. And then we're going to kind of having some basic of how everybody's basically are. And then we're going to start, because sometimes, I have a group that they already have some basics, so we can talk a little bit more advanced. And we have sometimes a group that really we need to start very scratch. So I just kind of quickly also, it's good to know all of you as you're here. And so kind of if you can introduce yourself, just talk a little bit about the topic at least, and what you already know. That would be nice. So I guess I have on the list the first, based on that, I think it's organized alphabetically. So the first person I have is called, I think, Banik. If I'm not pronouncing your name correctly, I really apologize for that. But yeah, so can you please go ahead and let us know a little bit?
Yeah, thank you, Professor Mehra. So yeah, so I think I had taken a class, software design, and that also has the design ideas, and I took a class for introduction to database and advanced database. That also has, I saw the UML diagram, and software engineering class that has basically UML diagram for object-oriented programming. So we are given to build some program, and we are asked to create different classes, and the Eclipse can generate the UML diagram so that we can show that which class connected to which of his children's, what is their inheritance relations, if there are any interface implementation. I think I did a little bit of this.
Okay, very good. So yeah, you have some basic knowledge. That's great. And so yeah, we're going to review all of them today, and then use them again in in the design of maybe a different software. So that's good. So you have some basics. So you remember, so you basically use just a plugin to automatically generate the diagram. You never actually draw any diagram using any case tool or anything like that.
I remember there was a tool that was we are given. I think it is at the paid version that also we can manually draw and plug that in. Which is very initially at the beginning we started doing that, and then when because that was a pretty small, I think 3-4 classes, but when we went to a more complex design, professor asked us, you don't have to do manually because you don't have much time. So okay, he showed us from Eclipse Marketplace, he showed us a plugin that could generate our existing class to the UML diagram. So that's what we did.
Makes sense. Thank you so much.
Thank you so much.
Sure, thank you. So let's go to the next person, and quickly, if we can hear from you. I think it's Regosa. I'm not again, sorry pronouncing any name wrong. Belay Regosta. Are you here? Can you hear us?
Yeah, he messaged his microphone is not working, I guess.
Oh, okay. So yeah, if you want to text us anything, that's fine. You can just tell us what you know, and then we'll read it later. And Chen. Chen, are your microphone also have issues? Or you good?
Sorry, I think he's one of the RU.
Yeah, hi, Professor. I'm
Oh,
Chen.
sorry.
Yeah, no, you're good. No, you're good. Yeah,
Okay,
yeah.
perfect. So
Yeah.
again, the next person is Gabrielle. Sorry. Gabriella. Sorry, Gabriella.
Hello, yeah, my name is Gabriella.
Hi.
I'm a student at UT Dallas. I was introduced a little bit to UML and also analysis in my software engineering class.
Okay.
It's been a little bit since I took that class, so it's gonna be really nice to get this refresher, but I do have some experience and I worked like with a group project on creating those designs.
Okay, that's great. Okay, perfect. So let's go to next person. Jan?
Hello,
Hello.
it's Ian.
Ian, sorry. I'm so sorry. This
I've
morning I
had
can't see very well. Okay, go ahead.
I've had a little bit of experience with UML in my software engineering class, but our professor wasn't too familiar with it, so we didn't get too in depth with it. We just kind of did a surface level overview of what UML was, and I've used OpenUML to make some basic designs.
Okay. Very good. So yeah, perfect. So that's good that, we have a different crowd. Like last year, I remember we had a student that they had no idea. So that's great. So we have some combination at least. So who's next? If I pronounce your name wrongly, sorry. Corey?
Hello, my name's Corey. I'm a student here at UT Dallas. I have actually no real experience with UML. We used it a little bit in our first and second computer science introductory courses. I haven't taken software engineering yet, though. My class schedule is a little unusual, but I'm excited to learn a little bit about it today.
Okay, very good. Thank you.
Thank you.
And we'll have next Lisa.
Hi, so just like Corey, I don't have any experience in UML, but I am excited to learn about it today. Thank you.
Sure, thank you. And Nicholas?
I don't have any experience in UML, so
Okay, and how about did you do any object-oriented programming before?
yeah, I have done object-oriented programming again in high school and in
Okay.
UT Dallas.
Okay, so perfect. Thank you. So I guess it was Nicholas, right? The last person.
Yes.
Okay, so Patrick now.
Yeah, can you hear me?
Yes. Hi.
Yeah, so I don't have any like formal experience with UML, but everyone draws diagrams for their projects and stuff. But so yeah, I see its utility.
Gotcha. Thank you. So and Rachel.
Hi, it's Rochelle.
Michelle. Okay. Hi. How are you?
Good, how are you? My experience with UML diagramming is through programming 1 and 2. And so we diagrammed, we made class diagrams. So, and then my experience with object-oriented programming is the same.
Okay, very good, very good. And I guess the next person would be Teresa.
Hey, I'm Teresa. I go to U Dallas, not UT Dallas. Anyways, I don't really have any experience with UML, but as someone mentioned before, like we've all drawn diagrams for our projects, so it's close enough.
Okay, very good. And the last person, I believe, Wakil, right?
Yes, that's correct.
Okay, hi, how are you?
Good, how are you?
Very good. Okay.
I have a little exposure with UML. I took my first software engineering class like 2 years ago. I think that gives me a little broad understanding about UML. So I'm a little familiar with that.
Okay, I see. Perfect. So that's good. So we have a kind of like a, we can go through the introduction a little faster because, I feel like at least most of you, not all of you, have some sort of background in software engineering, which is basically, that's what we're going to start. So we're going to do with the object-oriented analysis and design when we do the software, basically software engineering overall. And we quickly going to talk about one of the very common questions that I get from a student. What is the difference between computer science and software engineering? And so you kind of see this in this table that we kind of put it together, the things that are completely different from each other when you're dealing with the computer science type of problems and when we're dealing with the software engineering type of problems. Basically, they're both solving different problems for us. And you see that more computer science problems are going to be more, smaller, probably very specific. So you're looking for a solution that maybe it needs to be very optimal. And usually, basically, they're considered as team problems. And on the other hand, the software engineering for problems usually going to be kind of like a mass production. We get some algorithm in the computer science, and then we're going to use that now with creating Google, right? So we know the search and how the search is going to work. We have the algorithm for it, and then we create a search engine. So now everyone, they can do search on the web and find what they really looking for it. So the size and the aspect of the software engineering type of problems completely different. So it's going to become really, really, really large. It's not going to be specifically related to our domain, which is when we're talking about domain, we mean really the field of software and the science behind the computer. So it's more likely that we're doing it for other fields, other disciplines. We may doing it to help the billing systems. We're helping these days in our every day-to-day life, we use some sort of softwares anyway. Turning off your waking up, you have your smartphone with you all the way to opening your garage, making your coffee on all the way to just driving. Anything is pretty much, we're completely dependent on these softwares. And so those problems usually, we're just looking for the market, and the price is important for us. We're trying to stay below a certain budget. We need to get to the market, to our customers as soon as possible. Otherwise, we're going to lose the market. And so therefore, we're not having any profit out of it. The problems that, as I said, they're very large. And we're going to build during multiple years, 10 years, million line of code, multiple different group of people work on it. So it's just the scale of it is completely different with the scale that we're going to deal with in the, computer science problems. So it's not going to be that very technical. So basically, you can think about it as an infrastructure, as an environment that in the back of it, you have a lot of modules, components of computer science, like AI, machine learnings, all those algorithms that helps us. So those are like different components, different modules. They need to talk to each other, and then we're building this software to kind of hide all of these behind the scenes. So the end user that may not even know anything about science of a computer, they can use it still. So it's going to be user friendly for them. And all those complexity is going to be completely hide behind these softwares. And so that is going to be basically kind of like talking about the differences. So since we're dealing with this type of problems, and as I said, multiple group of people going to start working on same problem, just build on top of it. And we didn't really know how to handle it, right? When we started maybe like 200, 150 years ago, still our problems were small. But then we started like, building from like a little rooms to the entire city, right? So the software has become so large that it's more like a city now than it's just a small, house or a small building. So you need to have a very systematic way to approach it. Otherwise, we can easily forget what we did, what previous group of people did, and then we're going to build the same thing over and over again. So we're not going to have enough progress. So now we learn how to do things modular, how to find things that going to become abstract enough that they can be separated from each other, and then we can build on top of it, or you can use the same module, same service, same components over and over and over again for completely different softwares, for completely different disciplines to solve a different problem for a different group of people, but the same thing. So we already built this, so why we keep rebuilding it? So we kind of learn from other disciplines too that, we can kind of create these components and then integrate it with other components. So how we're going to make this integration easier, how we're going to learn how these, components are going to become like abstract enough and general enough that we can use them in other disciplines, other, components that they are other problems that they need the similar components. How we're going to see that, how we're going to make it as general as possible. And it's not going to happen in one night, or 2 years or 10 years, right? So it's a pattern, and it's really needed a lot, it's a lot of research, and we kind of find certain patterns, we find certain way of handling this, and then just going through all these softwares throughout the year. What are the failures? What happened that we failed? We spent so much money, so much resources, and what happened that it failed? So it's kind of backtracking or root causing of the problems, and then finding also the softwares that stay in market long enough, and they're still going to be useful and still going to be able to add things to it, maintaining it, and all of those. So this is happening during this like 100 years or 200 years ago. So it's still in progress. We're still learning, I have to say. So this discipline, the software engineering discipline, is fairly new. If you compare it to other disciplines, like for example, civil engineers, they have the background of, I don't know, maybe at least 3,000, 2,000 years of a human being, start buildings, a lot of different structures. And then they kind of document everything they did, document their design. And then we all kind of learned during this 2,000 years. And so now if you think about this discipline, like, as I said, civil engineers, there are not much things happening in their fields. So are not new things every second, every day, right? They're pretty much kind of, steady, like it's not too many things changing. It's completely opposite in our field because it's pretty new. We're still in the learning. It's kind of like a baby still. And, in this also kind of changing really fast. We learn new technology, and then with a lot of things that, we already think about it and used it as changing rapidly, right? So many things that we learned like 20, 30 years ago, we didn't have networks, we didn't have internet, we didn't really have the way to, smartphones and this many people using softwares. And so that was a different way to handle it. That was just only 20, 30 years ago. And now suddenly we're getting to the completely different situations that we have pretty much everyone, young or old, or, any type of people, basically, they're going to day deal with this type of basically softwares. So it's here we see some example of the problems that they're mainly going to be computer science problems, right? So like anything that's very mathematical, it's more like operations and needs optimizations, and we're looking for a very optimal solution for it. So we're spending time and money to find the best solution possible. And that's what we care. We want to do it the fastest possible. We want to use the minimum space as possible. And those are definitely going to be more technical and basically become computer science problems. So it's just some example of those. And then we're dealing with the completely different types of problem that, you know, they're huge, they're completely different disciplines. But we're using those knowledge and we're creating this application. So we can easily say that this is kind of mass production of whatever we learn in the science of computing. And we're going to apply that now, those knowledge, and then help people in different disciplines. So I have some class discussions because I know it's in the morning, so many of you are still kind of sleeping. So it's good to, you know, think about some of these and then before we move on. So as we just talked about it, so any of you remember what was the difference between computer science, software engineering, what are the focuses, and what are the differences between them based on what we just said, or anything else that you want to add to it? Anybody? Any volunteer? No? Can you guys still hear me? Okay.
Yes, I can.
Okay, go ahead.
No, I mean, I can hear you, sorry.
Oh,
What is your question again, Professor?
so you see the slide, right?
Yeah.
The first one. So what do you think the focuses between the computer science and software engineering, you know, respectively? So basically, what is the difference between them? What they focus on, what kind of problems they solving, you know?
Yeah, I think I might be right, but maybe wrong. But the feel that I have, the difference between programming and computers and software engineering is kind of very solid because they are not equal. Programming is a set of rules that we learn, and from the very root, from programming, from object-oriented programming, and everything. We are not really concerned here whether that program will be expandable in future. We are not concerned here whether it is going to be managed by multiple people, whether it's going to be you know, be adjusted in future with the needs from some other stakeholder. But in software engineering, because that involves a lot of people to work together to achieve a common goal, and which goal can be, you know, adjusted based on the requirement from the stakeholders. So here, so for software engineering, here we need a more human involvement, and there is more human interactions, and we want to build something that is more user-friendly. The people, people can understand the software, even people who doesn't have any idea how internally software works, who has no idea what is the programming and how to write a single line of programming, but still they should be able to use the software. But when you talk about just programming or computer science, it requires, you know, in-depth knowledge of everything that we have, from architecture, from everything, from networking, everything, from the knowledge that a computer scientist need. So that's all I see the differences between them.
That's great. So you pointed a lot of very good, basically important issues that we have, and one of the things that you just mentioned, the user-friendly and the quality overall. We're going to talk about the quality. Software engineering, we rely on it every single day that we wake up. As I said, like, you know, we wake up with, you know, having our smartphone or even our, you know, watches that, you know, alarms that wake us up. They're all having some sort of a software in it. So it's important that we can rely on them. So it's the reliability of this software is becoming more and more important. So, and, you know, there are lots of aspects in it, as, you know, the human being getting involved, and lots of people going involved, stakeholders going involved. And another thing that you mentioned that's very important, that the fact that these things keep changing, right? So requirements that we're getting from our customers that we're going to build the software for them, that is constantly changing. And we, we need to be able to make those changes. Otherwise, our customer is going to be unhappy, and then unhappy customers means that the program or the software is actually failed. So we don't want to get to that scenario. So we need to have a very systematic approach that we can deal with all of these different kind of problems that we are dealing with. And at the end of the day, we have a good quality software, and that is going to be reliable, secure enough that our customers and users are feeling confident to use it, and basically rely on it. So they're very, very good points. Thank you. Anybody else want to add anything to it?
I was just going to say that when I think of computer science, I think of foundational, more research. When I think of software engineering, I think of the more practical, more industry oriented of the two.
Correct, right? So basically it's more, we're using those knowledges that we gain in the computer science. We still need to document them, but they're not going to be as large as, and as complex as the software engineering problems. They're going to be written very nicely. Obviously, we're going to have a lot of paper about them. Every progress of it is going to be documented, but at the end of the day, they're going to be manageable. Software engineering, they're not like, we're going to use that component of the computer science maybe inside a big software. So like these days, you probably hear a lot about AI, machine learning, and those are computer science problems. And those problems, when we have the solution, we have the algorithm, right? Then we can apply it, we can use it, and then we're going to build the application that using those AIs, using those mechanisms of the basically computer science problems, and then solve a different problem for different completely different disciplines. So yeah, all of you getting a very good point. So I guess now it's very clear, the difference between these two, because I know sometimes, especially when the younger students, that they want to pick, or should they go to computer science, should they go to software engineering, which one is, what is the difference, right? So sometimes it's not, it's not clear cut for some of us at the beginning, but now you kind of can probably feel the differences. So they both help each other. So basically, when we are going to kind of discuss so I guess we already discussed the programming in large, right? So, software engineering basically is kind of math production, right? So we're now going to build the really, really, really large programs, which would usually not have that in the computer science problems. But the last one now, let's discuss a little bit about that. What is the relation between software engineering and computer science? Can we have one without the other one? Can we say, we have computer science, we don't need, software engineering anymore? Or we can say, we have already software engineering, so what is the point of having computer science? Do you think we can have one without the other? Are they going to help each other at all? What is your thoughts about it?
When I think about the relationship, what I see software engineering is building on top of what computer science introduces. It's taking what could be more academically focused, more research focused, and changing it and applying it to a more mass, more industry oriented way, so that it can be used for more than just academics, more than just research.
Correct. Anybody else want to add anything? Everybody agree, right? No objections, right? So definitely we cannot have one without the other. And so they're helping each other out. And so basically without computer science and all those problems that it's going to be solved in there, we cannot have, using those to solve other disciplines of other people's problems and create software engineering. And then without software engineering, we cannot really apply any of those things that we learn and we work on them in the computer science. So they really need to kind of coexist with each other, helping each other out. So, and you cannot have one without the others, obviously. So hopefully this is also very clear for all of us, and it's not going to create any problem later on. Any question before we move to the next slide? So now let's have a definition for the software engineering. So many of you probably see some definitions. So another thing we working on it, and we're not really there yet as far as the software engineering is the definitions in different, the vocabulary basically. So we have a lot of keywords, and we kind of start using it maybe 10 years ago differently. And then as we move on and we learn more in our research and in our science behind it, we'll come up with a better definition of it. But then we start reusing those keywords. So sometimes, it's not clear when you're reading a web app, when you're reading it from or reading a book, you don't really know when they're referring to a particular keyword, what they really mean, what is the meaning behind it. So we have this problem with the process and methodologies a lot. Like, so you read about it on the, on the internet or any books, and then you feel like, you can use both of them in any senses. So there's no difference really between process and methodology, right? But when we're, as we move on, we kind of say, oh no, they're different from each other. So hopefully we can get to a point that we do have a really good dictionary, that we all can kind of refer to it and then say, okay, this is the definition of software engineering. This is the definition of AI. This is the definition of robotic, right? So we don't really have, it's kind of mixing, and all of them kind of used sometimes interchangeably, and which can create confusions, right? Sometimes we don't really know what we're talking about. So this particular definition of the software engineering is coming from Dr. Khan's book, and I guess we can see where he got the definition from, what is it? I mean, source of it, but it's really from very 20, 30 years ago. And that's because that was what it was very important when you're creating software product. So let's review this. It makes sense. It still is not completely wrong, but you're going to see that some of these aspects of it, it's a little bit different now when even we think about it nowadays with all modern technology and everything that we have in front of us. So the software engineering is a discipline, and the focus of it is going to be anything that is related to the research education and the application of engineering processes and methodologies. So the goal is to increase the software productivity, software quality, reducing the cost of the softwares, and going to the market as fast as we can. Basically, time to market is going to become important. So as you see, we do talk about some of the qualities, but the qualities that is focused on here is, productivity and going to the market as fast as possible and reducing the cost. So all of them are still important, but like the quality now, all those metrics that we're working about, and then saying a software is now have a good quality or is it's a acceptable quality is a difference. So first of all, as far as going to the market, so if you think about 30 years ago, how we're going to ship a product to the market? Anybody have any idea how they would do that? If you create a software, now we're going to, ship it to your customer, how you would do that? There is no internet. So how are you going to do it?
Maybe we just build a desktop app and just drop it to their local machine, and that will get the install on their machine.
So basically you need to have a way to store it, disks, right? And then create a lot of them and then ship it overseas, ship it to all the, end customers, right? So that would be very costly. And of course, and then you need to make sure that you get to the market as soon as possible. So that's why you kind of hear, probably heard, that we had this, first version and then the alpha version that is going to solve a lot of problems that they're, feedback from the customers. And it could take a year for getting a new version of a software that, the programmers already work on it and solve the problems, right? So it would be expensive because shipping them, it is expensive. And then it would be also the time, it would not be as fast as we can see now. So now think about it nowadays, cost of shipping a new version to your customers. Is there any cost associated to that, really?
Well, the biggest cost really is just how do you keep it up? Because a lot of things can be installed online, but you have to pay for posting and having it available online. And so,
but if they are a member already, right? Even if you were a member before, you still have to wait until the product shipped to you. But if you're a member right now, some softwares are even free. It's just a push to your system, right? So think about all of your smartphone, right? Any new version is just come to you automatically. You don't even sometimes notice that it's a new version. If it's an internet, then you're just going to click on, you know, a web browser and then download a new version, and that's it. So shipping it to market, you know, cost of it is zero. It's close to zero, right? So some of these are kind of changed. So that's what I was trying to say. It still is not completely wrong, this whole statement, but there are things that changed. And the quality of the software nowadays, when we think about the quality of it, the very first things come to your mind. What do you think? What is going to be the first thing come to your mind when you're thinking about the quality of a software that you think you're going to use?
I would say UX, UI is probably one of the most important qualities. If people don't like looking at it and people don't like interacting with your software. No
So
one's
being
gonna really wanna
user-friendly,
use it.
okay, what else? But before you even pay for it, you're going to go do what? Some research. How are you going to do the research about it? What is the questions you're going to have, you know, you want to see like what other people say about it. And then, oh, okay, I can pay. Like imagine you want to, you know, some simple things as like a, you know, a camera, right? So that you're going to install in front of you, like a Ring or something, right? So you want to buy one of those. What are the things you're going to search and see, like even it's going to work or not, right? So how reliable it is, right? So I'm going to pay for it to do this certain things for me. Is it going to do it, right? That's the very first things coming to you, and can I rely on it, you know, because I'm not going to be home and I want this to basically answer, you know, to the whoever's come to my front door. So make sure my kids are not going to open the door or whatever, right? So there are things that, you know, change again. So the meaning of the quality of the software is completely different because nowadays we're going to deal with them every single life, you know, and it's basically kind of can be, in some sense, it can be even scary. So the quality of them is mainly going to be the reliability of them, how secure they are. That's also important for all of us nowadays. How you know, what kind of a privacy they have. Like some of them are holding our, you know, very important information, and so how they're going to keep it as secure as possible. You know, how they're going to make it all the privacy aspects of it, take care of it, and stuff like that. So all of those are kind of changing, but of course being user friendly is also very, very important. And so how we're going to come up with the, you know, software is user friendly, people can use it, who's going to use it, right? You know, people are going to have used it are kids, people that are going to use it are basically are, you know, have some sort of disabilities. So what are the things that we're going to add to this software that can help all of those users to be able to use it so it's usable for them? So those are going to be also very, very important. But at the same time, we're still going to work on these softwares, and then we know they're going to become just larger and larger and larger, and there are more people going to work on them. And so you know, in order to keep them reliable, we want to make sure when we integrate these softwares on top of each other, we test them really, really good. And so we need to have a very good mechanism from the very beginning when you're starting the design. Think about how scalable it's going to be, how I'm going to maintaining it. So one of the things that I have to say is very, very more important than anything else is going to be maintainability of these softwares, right? So not only we're going to make them productive, but also we want to make sure we can maintain them. So anybody have any idea what we mean by maintaining a software? What software maintenance really means?
It doesn't mean like keeping the application up to date in terms of security, vulnerabilities, potentially adding new features or fixing up old ones that are bugging out and then making it work for upcoming and new operating systems.
Yeah, I think you pretty much pointed everything. Anybody else want to add anything else to it?
Could it be like refactoring as well?
Yeah, so yes, correct. When we're writing a software at the beginning, maybe we're not going to write it very nicely and clean, right? So definitely go back and refactor, do documentation, all of them is going to be part of the maintaining it, because if you don't do that, then other people cannot read it. And then when they can't read it, they cannot understand your code. And when they don't understand your code, they cannot maintaining it. So it's kind of like before even we get to that, you need to make sure you do take care of it. So basically those are the steps to get to that point. So basically what I'm trying to say is that we're not going to build any software from the scratch anymore. The softwares are too big, and we already solved a lot of problems that we do not really need to solve them again, right? So we just can use that module, use that component, and then just build on top of that. So basically, pretty much all of us as a software engineers, when you start working on industry, none of you pretty much not going to use write a software from the scratch, right? It's always going to be building on top of somebody else's code, which that means you need to understand that code. It means that code needs to be maintainable. And if it's maintainable, you can add more feature to it. You can update the features that's already there. So, and so you can keep it up to date and add, features, or add, be able to even communicate with the new technologies coming to the market. And all of them, that means that if your software is not maintainable, you'll not be able to do that, and then you're going to be off the market. So there are many softwares that used to work and they were just basically very hot in the market, and then suddenly when new technology come and they can't really keep up because they didn't really build in with that mindset, and then now we're trying to add these new things to it, they can't, because if they miss, basically if they change something, everything else is going to break. And they don't have good documentation for it. They didn't really have any testing for it. Those people that work on that software are no longer available, that we can even go talk to them. It's like what this software is actually was doing, So you're just scared even to touch them, because if you touch them, it's going to break. We have some codes that we call them, or programs that we call them legacy programs. Anybody know what legacy programs are? Anybody heard about those?
Isn't legacy code just code that's kind of become so old and hard to maintain that people are scared to touch it?
Exactly. Like lots of things build on top of them, and they become like a core piece. And then nobody knows even that sometimes the languages that those programs written, nobody even know them anymore. And then there's no good documentation. We don't really know if you change anything, what is going to happen. It's working right now, so let's not mess with it. So those are the codes that nobody even go ahead and touch them, because you can create a huge problem later on and you cannot really fix it. So those are basically, some of the things we also deal with it. And, you probably hear sometimes in some of the big banks, the core part is written in COBOL, for example, and they really sometimes need people with the knowledge of COBOL so they can go help them, right? But they're, usually it's a very, very bad idea to touch those type of codes that you don't really know what happened in them. But as long as they're working and everything that's on top of them is still working, so you don't want to touch them, right? But then if you have to, at some point, then you probably have to go and start from the scratch, right? So that happened to the Microsoft one time, right? That they start building it, and then at some point they realize, no, this code, we can't really add anything else to it. So it's just messed up completely. And if you have anything else to it, the whole thing is going to break. So it's kind of ripple effect, right? So it was so bad, that ripple effect was so bad that they decided to just kind of rewrite everything that's going to be more efficient, because when you're changing something that you don't really know what is happening in it, you're going to create huge mess, right? So sometimes it's better, when you see those kind of codes, spaghetti codes, you're just going to go and start from the scratch. It's a lot easier. Another problem we have with maintainability is the testing, right? So if you write, whenever we start writing any software, nowadays we ask people to please, as you write even the simple little method that you're writing, first think about how I'm going to test this, then start writing it, right? So test-driven development. Anybody heard about that keyword? No, nobody heard about test-driven.
I've heard of it. I haven't used it too often, but I think it's a good practice.
Yeah, test-driven development is basically telling you that first implement your tests and then start implementing the actual code. So that makes sure that when you're implementing now your code, you think about the fact that this code needs to be testable, because many times we're writing codes without thinking about the testability and readability of this code. And then we feel like, oh, we've done our job, right? But then nobody can read it, nobody can test it. And we probably cannot have time to talk about what can create problems for testing, but just think about the very simple problems such as, switch cases or if else statements. Every single time that you create another if else to your program, you create a completely different branch to your program. As a tester, somebody needs to test that branch as well, right? So all of these branch needs to be tested. So if you have a software that have 10, 20 different else statement in it, it isn't a scary code, right? For testing. So if we know as a programmer, if we also know how testing is going to be complicated, if I write a code like this, if you have that knowledge, then you're not going to write the code like that, right? Because you know it's going to be really hard to test it. It's fully testing it. It's almost close to impossible. So why are you going to do that? And then you're going to rewrite it in a way that is more testable, right? So, you know, just so you see, like we're talking about a lot of different things and that are important that maybe it's not really, you know, it's hidden here, right? We don't see it. So the definition definitely going to need a little bit of a change and maintenance as we're, you know, moving to this, you know, software engineering, and we learn more and more. So as we talked, we noticed that the challenges that we have with software engineering, we already kind of, you know, touch base all of these things, you know, the fact that it's too big, the fact that many people working with it, you know, throughout the lifetime of those softwares. And there are people that were going to work together. They're sometimes even overseas. They're completely coming from different background, different knowledge, different disciplines, even sometimes. And so they're going to have a different understanding. And sometimes even we're not even talking in the same language, right? So we have a lot of challenges of conceptualization, how you're, you know, what are our background knowledge, how you communicate with each other, right? So how we understand each other, you know, it can be creating, you know, problems. Sometimes even we have that problem with our own customers that they're telling us what they want, right? Because very first thing we need to do before even we start any software is to understand what our customer needs. And then when we understand what the customer needs, then we start, okay, how we're going to help this customer. So the first part is always what, right? And sometimes this communication barrier that we have with our customers, that we're not part of their disciplines. We don't really know what they're doing in their day-to-day life. Some keywords that we use in our disciplines completely differently, they're going to use it in a different way. They have a different meaning in their disciplines. So we have this huge communication barriers, and they don't really sometimes know or cannot tell us what is the real problem is. So we're going to talk about a simple example that hopefully helps you to understand this communication a little bit, at least in a sense that we have this communication problem with our customers. So imagine you're having just go through this story. Imagine we have a farmer, and this farmer have a problem. So it's coming to us and not happy, and it's, you know, telling, and imagine we are a magician, we can help him in any sense. So we tell him, okay, tell us what you want, I'm going to help you. And then they're going to say that, okay, it's just raining constantly, and it's just ruining our products. It's just not let us do our job, right? We're farmers, we need to, we need this rain to stop. So what we're going to do as the magicians, right, the software engineering for them to help them, is that we somehow needs to stop the rain. Well, we don't really understand what is the main problem, because they didn't tell us the actual problem, right? They just said that we want to stop the rain. So what this magician is going to do, to just solve the problem, one of the solution, it would be just, instead of raining, it would be snowing. Did we pass the requirements? Is it raining now or not? Is it raining? Yes or no?
I mean, technically it's not raining.
It's not raining. So we did pass the requirements. So if the requirement is that stop raining, we did stop the rain, and now it's a snow, right? But did we solve any problem? No, right? Because we didn't even understand what was the main problem, right? Because we're not farmer. We don't know what is wrong with raining, right? We have no idea. And the farmer didn't tell us that why he hates the rain, why we want the rain to stop, right? Just tell us that I want this rain to stop. So this is happening in And this is a very simple problem that it feels like, it's obvious. We don't know, right? So because we're working for a completely different discipline, and then they come to you and they say, I don't want this, I already use this software, for example, I already had this software, and I want this software to stop doing this, right? Whatever they do, like creating this type of report, I want it to be stopped. They don't tell us why. They don't tell us the main actual problem. So that is going to be one of the main problems, because if you don't understand what is the actual need, what is the actual problem, and you just kind of go based on whatever they tell you, okay, I want to stop the rain, then everything that you build, all of these software that you build is not going to help, because it's not even solving anything, right? So it is very important to have a very good way to communicate with our customer, but the same exact scenarios can happen between people in the same group or people with the same project. So because in a project, when some project is so big, we may have a completely different group of people working together. We have a human resource, we have a software engineering, and then we have a maybe mechanical and electrical engineer working together, all on the same product. And they're all going to have a different way to communicate. And communication problem can cause a lot of issues. So even within our team and within our projects, the communication can cause issues. So that is one of the big problems, and software engineering is for one of the main reasons it's there to help us to communicate with each other, right? So, and then the last thing is the coordination, right? So within the team specifically, and then within the project, we definitely need to coordinate together very well, right? So you don't want two teams at the same time working on the same thing, duplication, right? So that should be a way somebody knows that we're doing duplications here, or it can be a part, like in one of the requirements of the software that is completely missing, right? Because we didn't really have a way to know who's going to do what. Another thing that can cause problem in the coordination is that the fact that we're going to, like, one team is going to wait for the other team for a long time because we didn't really organize the job or assigning the task between this team, that they can work independently without the need to wait for the other team. Like our team maybe waits for a solution from the team number one to even start our own work. And then, so we cannot do anything because we don't have that, right? So how we're going to organize this work in a way that we know how we're going to break this task, like break this big problem to the smaller problem that basically each team can individually and independently work with it. But then at the same time, we need to, at the end, add them all together. We call it integration. And how we make this integration easier, because if we do work on the different things, but then we have no way to integrate them back to each other, then we're still not, we did kind of nothing again at the end of the day. So it is important to have a very good plan, know what we really need to do, how we're going to break it to the independent pieces, or what we call components, modules, right? The modular-based, component-based part, it's very important. And then how we're going to now easily integrate them. And as we do, how we're going to test it. It's because we need to maintaining it later, right? So there are lots of things going to be involved. And again, none of them is going to happen during a, short period of time. It can be, in a lifespan of 10 years. Some people that they're working on this product, 10 years ago, they're no longer even there. And so we need to have the good way of the documentation so we can go back and see what happened, and in very fast way, right? Because if it's also not easy to understand, then you can really rely on it anymore. So that's a problem, right? So software engineering dealing with a lot of problems. So that's why it's also very important for all of us to get ourselves, get the knowledge. But then sometimes some of the students say, okay, we maybe I was working in industry, I was working in programming, our product was very successful, and I didn't have any of this knowledge. I was just doing my work and it was working. So at least somebody somewhere, have some knowledge. And you hear about that frameworks a lot, right? That's one of the main reasons we have frameworks, right? Because the fact that we know we have people that start programming, and they don't really have maybe deep knowledge of all of these things behind the scene in the software engineering. And then we want them to start working, and you know, we need their help to build this, you know, software. So how we're going to make sure at least our software is going to be in a good shape, you know, in maintainable shape, even though that different people with different knowledge and background working together. So one of the solution was creating, and that also is a software engineering solution for the software engineering, again, is creating those frameworks. So frameworks forcing the individual without even having any knowledge to follow a certain pattern that we know those patterns at the end are going to make this software more productive and have a better quality overall, so we can at least go back and do some maintenance without, you know, completely break everything. So whenever it's needed. So the frameworks also are very helpful. So as you can see, the solution that we see here is that, first of all, having the steps and having some methodology. So as I said, if you remember at the beginning, I said that we have some keywords, and then when you just Google them, or just reading some, you know, older books sometimes, or different books even in the software engineering, there are some keywords that we do not really understand the actual meaning behind them sometimes, because they're used interchangeably in different you know, documents. So here, when we're talking about process, we're going to focus on these steps. What are these steps? Step 1, 2, 3, 4, right? So that's what we mean by process. So, and also basically it's going to be you know, or we can also kind of think about it as what are the steps, right? So the keyword what, it's coming to the picture here. So the process is going to tell us that what are the steps. And then when we're talking about the methodology, the meaning of it is going to be different. So the methodologies are going to tell us that for every single step, how we're going to implement that step, how we're going to go about it. So the methodology is basically going to use the keyword how. So for each step that we have in the process, how we're going to do it. So, and then these are going to be all both for analysis and our design. So those are, we have steps for them, and we're going to see what we know, what we're going to do and how we're going to do it. And there are different hows sometimes. For one single step, we may have multiple different methodologies, right? So it's kind of sometimes become like a mix and match. It depends on your software, depends on the expertise of your team, depends on you know, your knowledge, your background, your resources, your time, your budget, lots of things. You're going to pick different processes and then combine that with the different methodologies. So that's how you're going to kind of starting the whole process when you start working on any software. To solve so that's going to help us for the, you know, maybe in many things, it's specifically probably going to solve the problem of the conceptualization, the fact that we don't know, we're coming from different, you know, background, and we don't really know what, you know, what is going to be the next step, what we need to know. So at least we have this in front of us, kind of like a chart telling us what we need to do next, even though we don't really have a fully knowledge of why we need to do that. Somebody started come up with this, and then now we say, oh, all these teams are going to work through these steps, and these are the methodologies they're going to follow. So, and again, this is going to be, you know, when you start in any project, you start in any companies, kind of sometimes become the culture of that company, like, you know, always they're going through these, if they have, you know, because they're dealing with the similar types of problems, they have different teams, and this is how they're going to kind of come up with this process and methodology. So mix and match in that way. Or sometimes they're going to be based on different product that they're going to build and how new it is for the team, how much time they have on all of those. So it's really going to be different in every product. And then the second thing that we see here, and again, it's going to be more focus of our discussion, you know, today and then on the Friday session is going to be the UML. So as you can see, UML, it's going to help us a lot, because it's not only going to help us in the communication, it's also going to help us in the coordination, because when we're dealing with the communication, as you remember, we said the fact that we don't have a similar way to communicate. But when we have visualized that, right, or we have a model in front of us that we all understand this model, we don't really need to talk anymore. I can understand this model without even talking, and you can understand the same exact thing without even talking, because we're using this model and the model has a specific meaning. So it's very, very important. And this is something that I feel like we don't emphasize on it maybe too much, or it's just kind of boring for some of our students that are so smart and they just want to start jumping into coding and they don't care about the modeling part. But you have to keep that in mind, that it is very, very important process. And it's really going to help you with anything, even if you start with a simple software that it feels like you already kind of know in your mind what is happening. If you're just drawing it for yourself in front of you, that's going to help you like a lot to how organize your work. That is going to be later on easier to understand, easier to change, easier to maintain, and easier to test, right? So it is a very important. And so what is UML really? Like, anybody know what this UML is, a stand for?
Unified modeling language.
Very good. So it's unified. That means that we all kind of, everyone going to use it. It's modeling, it's visualizing something, and it's a language. So what do you know about a language? What do you think the very first thing about the language? What the language have that make it a language?
Nouns, verbs, things that like can express communication.
Exactly. So basically some keywords, as you said, and some structure to it, some rules to it. If you don't follow those rules, if you don't follow those structures, if you don't follow those keywords, nobody understands your model, right? So it's a critical, important part. Like, again, this whole modeling part is sometimes a hassle, sometimes a lot of work for us. Is there to help us to communicate with each other, right? Easier, like, because we all human beings, it's easier for us to understand things visually than reading it or talk to each other, right? So if this whole thing that is there for us to help us communicate with each other, if you don't do it correctly, is it going to help us? No, because nobody can understand that model. You're not following the rules. You just draw something, whatever you want, whatever shape you want, whatever figure you want, and you're hoping that whoever's going to look at it, understand it. So guess what you was trying to say, and then we're going to get to the back to the same problem, right? If we want to, we want other people to guess what we're doing or what we're saying, why we're going to go through this whole hassle of drawing this diagram. So then it's very, very important. And sometimes students ask me if really in industry people do that, if they really go ahead and do modeling, again, in a way that we may be just emphasizing on it too much on our classroom. So keep that in mind. People that they're working on industry usually have expertise. They usually work on a similar type of problem over and over again. Maybe in a higher level when they do architecture, when they do their actual analysts, they're definitely going to do some modeling for sure. In the documentation, they do have modeling. Maybe as a programmer, like, the lower level, you may not see it because basically they're telling you what to do and you have a structure, you just follow. Again, so it's kind of methodology. But as you're going to the higher level and you become a manager, you become a leader of the product, you need to have a very good vision. What is happening? And then things are larger and bigger now, and you need to have a good understanding. So if you don't have those models in front of you, you can easily get lost of what I was trying to do and what is going to happen next step. So they definitely do some modeling. But again, it's really also back to the type of a problem that you're trying to solve. Maybe in the computer science problems, we don't have too many changes, right? So the model is not going to become that important, and it's not that large, right? So maybe we already can just document something and that's going to be enough for us, because that's the whole point, communicate with each other, to understand what is happening before, so we kind of be on top of it. But then we're dealing with software engineering and specifically problems that they're going to keep changing, and then you keep building on top of it, and it's going to stay in market for 10, 15 years. And again, you get larger and larger and larger with new features. You definitely need to have a very good way to communicate. So you need to have that. And then coordination. So how this going to help us in the coordination? Anybody have any idea how the UML diagram can help us for the coordination?
you talked about dependencies previously, and then also I would imagine scheduling as well, maybe.
Correct, right? So when you're very good point. Thank you. So basically, exactly, when you have this diagram in front of you, you can have a good understanding of how these different parts are communicate with each other. And then if you kind of maybe sometimes even you change your design a little bit so you can make the components that are independent from each other in a way that they can actually be done with the completely different teams. Even each team, if they even have to wait for the previous team, they have something to start work on it. Like they can maybe create some dummy things, right? At least they have some format and what is going to be sent to them. So they're going to start with that. Like, you know, it all going to give the whole thing much more clearer for everybody. And then when they're trying to integrate things together also is going to help us, because now we know which part is going to be integrated to which part. And we have this whole model right in front of us that helps us to do that. So these are, you know, another things that, so you see UML is very important. Another thing I want to say that this language, so as I said, it's some rules associated with it. So the one that we're going to talk about it in this class is going to be the diagrams. The UML basically is a specification for 2.5, and I shared the links here, so we're going to follow that because, you know, the different version we learn, again, that's the same thing. We learn from our previous mistakes. We're going to solve it, and so we have new technologies, but now that needs to think, okay, how are we going to now show that in diagram? Maybe 20 years ago, we didn't have that, right? Now we have these types of systems that how they're going to communicate with each other. So how we're going to draw that. So there are new things also sometimes added. So the one that we're going to focus and all the rules and the diagrams that we're going to talk about them in this class are going to be based on the UML 2.5 specification, and you're going to see the link. So the last thing here, as you say, is about tools, how we're going to automate things and how we're going to get support in all of those steps of the process in different methodologies we're going to use. So tool automation is also very important. So we basically, we want, you know, we have these huge softwares, and so we need to make sure we have them somewhere that they're safe. We're not going to lose them. So some of these tools that you hear, like version controlling, right? So they're very important because it is common, even with the simple software and IT software engineering courses or computer science courses, Java or C++, whatever. And you see students, and many of them come to you, on the day that they have to submit their project and say, my computer suddenly had something to it, some problem happened, some virus happened or crashed, or I lost my computer. Somebody, basically, I just lost my code, like the entire code. I don't even have it anymore. So imagine that happening in, larger scale product, and then suddenly even one component or even the whole thing is gone. And so you don't have any copy of it. And then how are we going to copy that, right? How are we going to keep the track of what was the last version? Sometimes I see on the, students, they're showing me their work, and like, they have different folders with different names on it. And maybe sometimes it has dated, or sometimes like version 1, version 2, version 3, right? So they have different bunch of folders on their computer that they have different versions, and then they don't even know how to compare them, like which one was the last, if they forgot to, numbering them correctly. So even with a simple project of the class that is maintainable by mainly one person, they're usually very small or medium-sized software problems, you can easily get lost. You lost your code, you don't know how, you get back to it, you don't know how it was working, So we definitely, you can imagine for like large software, you need a way to have those somewhere safe. So there are tools to help us to do that. And then we just talk about the integration. As you integrate things, you can easily break things, right? So how we're going to integrate them and making sure we're not breaking anything. And that can create a lot of problem with us if we don't automate those things as well. So testing and automation and having everything in the same place, those tools that helps us to do starting from even requirement gathering, that helping us to make sure we're not missing any requirement, we don't have duplication, the requirement, we don't even, we have even understand the problem, right? Your root cause analysis and all of those. There are all different tools that can help us And then all the way to the fact that now we're writing one single method, one single class, bunch of classes, and then now overall the whole component, and now how we're going to integrate this component to the next. All of them, if you have an automation in place, is going to help us a lot better. So you're probably going to hear a lot of different keyword, a lot of things, right? So even IDEs are there to help you through this process, right? So you compile, it's going to give you compile error, and then you're going to have a lot of warnings. You're going to try to solve those warnings. You have a static analysis of your code, and you're going to start dynamic analysis of your code, which is going to help you to do testing. And then you find some different types of testing that the compiler cannot find it, runtime testing. Then you're going to basically, as you know, making sure that this part is working. And then we integrate that you have to do the same thing again. That's going to become integration testing. So you're hearing the testing tools. We just talked about the test-driven development. We talked about version controlling. Anybody heard about any version controlling tools? You ever used any of them?
I've used Git before, and I've heard of things like Subversion. I think that's the name. But
yes, yeah, there are lots of them, but the Git and GitHub are the most common one these days. And so basically, because we had one, we had a different, again, back to the different architecture and different technology. But the idea at first was, okay, we have one server and everybody, put their latest version on that server. And, but then that server can get lost or get, broke, or something can happen to that server, right? Then we have the entire thing lost. So that's not a good idea. Then they say, okay, we're going to have a bunch of servers, and then we're going to copy these servers every year, every day. I don't know, depends on how, how the software is, into another server. And maybe they put these servers in a different part of the world, making sure that, we're not going to lose anything. But then that also, was creating other types of problems, the size of these softwares and how they're going to, make sure that this whole thing, maintained really nicely. We're not missing anything still, and we can keep track of all of these, like, because the software is getting larger and larger. So then they just started thinking about other ways. So the GitHub technology is kind of, and GitHub is basically kind of like everybody have the softwares, but then just not the whole thing, because it's going to be very large, but at least have the differences. So that way we're kind of making sure that is not only one single place for it. So it's going to be on the cloud kind of. So it's just depends on the technology change. We're learning new things, and everything is going to get improved. But as your friend says, get up, make sure you make yourself familiar with them. Make sure you go ahead and start using it. There are lots of documentation available for you to do that. And keep that in mind. In industry, nobody is going to, or in the academia, unfortunately, we don't have time to go through these tools, because these tools keep changing, right? We just focus on the core things, the things we know are not going to change as often as those tools. So learning tools in our field, it's something that is solely our own responsibility. So we need to make ourselves familiar with what are the tools that are very common right now in industry, how we're going to make ourselves familiar with it, and start just doing it. Being self-learner and motivated, it's a very important thing in this field. Otherwise, you can easily become basically overwhelmed after some time with all these things you need to learn suddenly, right? So you just have to keep constantly trying to learn new things. So make sure you make yourself familiar with all these different tools that, if in any classes you're going to be introduced, and we may or may not be able to have time to even work with that. So that's one of them. But then we also have what we call integration, or basically continuous integration. So anybody heard about those? You know what the continuous integration means?
Yeah, my experience with continuous integration is that you're constantly trying to improve or involve all the components in a project.
So correct. So basically that's what normally going to happen, right? So as you're building this, different team, then somehow we need to integrate them together. But what I just pointed out is that this has to happen in a way that is going to make sure, as you merge these things, we're not overriding each other, where we're not creating any problem in this software, right? So we're doing it in a very systematic way, and there are tools for us to help us to know that if we merging these things, we're not overriding or basically removing. So we have no duplications in any sense that they can get merged and then get corrupted basically. Or as we integrate also, we like to be able to test the whole thing again. So usually when we use continuous integration, we had also the entire setup of our test there. And so we're not only testing each unit, each basically component, but then as we integrate them, this continuous integration is going to have those automatic basically testing built in it that is going to, and that takes time, right? So at the beginning you're going to build all of these things to make sure everything is working and is in place, but then over time it's very, very helpful, because now that these teams start merging their branches, for example in GitHub, or merging the different components together, this test is going to go in the background and test everything. Sometimes it takes overnight, and then it's come up with a report and then telling you if it's safe, to merge things, nothing broken as you merge them, or it's not. So it is a very, very important tool for basically large softwares. And it's like sometimes we feel like however we would be able even to do that without the help of these automated tools and these supports that we're getting from these tools. And then also all of those methodologies we learn, like we heard about agile, test-driven development, all of these, just helping us to do these things, all these jobs more efficiently, and making sure at the end of the day that the whole quality of the software is, in a very good, quality that we can, still maintain, change, and, still at the end, the software is still going to be user-friendly and answer the needs of our customers and all the changes, and also is still being reliable and user-friendly. So I guess a lot talking about all of these, and again, I can't emphasize on them enough, because again, that's the main reason that we even go to object-oriented programming. Because sometimes I'm teaching software engineering, and sometimes I hear from a student that I force them to use Java or force them to use object-oriented program and design in an object-oriented way. Even for a simple software, they feel that it's so simple. I can do this with the JavaScript or Node.js in one day and be done with it. Why you want us to go through all these hassle of creating this diagram and then implement all of these codes? And I have my answer to them is that we don't have time to go through a very, very, very large problem to show you how important it is to follow these. We're pretending that this is a small problem that you're working with it as a team is as large as it needs to be. So, and then you're trying to practice of these concepts on those softwares. And I know that many times, if the problem is not very big, it's not going to need a lot of changes, you don't even need to take the path of object-oriented. So the object-oriented is not the solution for every problem, right? Obviously, it's certain type of problem that requires software engineering to work on it in an object-oriented way. And whatever we talk about it, we're emphasizing on those types of problems, right? With problems that they need object-oriented, otherwise they're going to fail. The problem that they keep changing, that you need to be able to change them. The problems are so large that you cannot keep track of them if they're just basically going to be not documented enough and not using automated tool for them. The problems that are going to be large enough that if you don't understand them, if you change something, everything else can break. Bad design, not having diagram, not having a good vision about what is happening in the code, and then suddenly you're going to break everything. So that's why we moved from functional programming for those problems to object-oriented programming, right? So how many of you are familiar with Java, for example? Just want to kind of go over it, like, just quickly. I guess that this Zoom also have to have a way for you to raise your hand. I'm using Teams nowadays a lot, so I'm not sure, but just raise your hand if you have that feature, and then tell me that how many of you know like Java, and how many of you know JavaScripts, and how do you understand the difference between them?
In terms of JavaScript is it runs on the web compared to Java, which is more of a server-side thing. The name comes from marketing to make JavaScript a little more popular, and then JavaScript isn't entirely object-oriented like
It is
Java.
not object-oriented at all.
Yeah, it
No.
has
So
syntax.
that's a problem I have with the students. Like, I'm going to write it in an object-oriented way, but you can't because it's not object-oriented language, right? And so many concepts that we have in the object-oriented, you cannot even apply. It's basically, they don't, this is not designed for object-oriented programming. So, and so yes, it's a script language, right? So, the Python, JavaScript, PHP, all of them are script language. So you may be able to make them look as modular as possible, as creating objects in them, even though, but they're not really object oriented. So the way that they're working with objects is different. So when you're trying to learn at least this concept, you want to go with a very basically pure object oriented language that you can be able to see and you can be able to apply all those concepts. Then you learn it there, and then you have the core, you have the base. Then if you now start doing it with PHP or JavaScript, you know what you're doing because you understand the difference between object-oriented and then script languages and basically functional programming. And there are different solutions for different problems. Again, nobody said that the script languages are bad. Like, they're helping us hugely to solve a lot of different problems. But specifically when we're dealing with large problems that again, require a lot of changes, they're not going to be as efficient for us because, you change things, everything else is going to change. And so again, we're trying our best to make them as modular as possible, but they still are not going to be as efficient, as object-oriented as then, object-oriented languages. So we need a whole spectrum. So nobody going to say only object-oriented and nobody going to say only script and functional programming. It's just a whole spectrum, depends on what you're trying to do. Sometimes you have to combine them, as your friend says. Sometimes or most of the time, the backend part that do all the process and require a lot of changes whenever the customers need change, because that's the core part, that's your actual model part. That's the part that do the process, do the main job. That needs to be object-oriented. But then as you go to the front, which is like just a script, and you want to be lightweight, you want to be able to just, interact with your, end users, that can be script language, and that's going to work pretty fine. And that's what basically happening also in industry. But there's like there's a big lane or big part in the middle, usually, if you think about, for example, interactive type of systems that maybe like any web application or any software that require interactions between the users and requires some backend processes, and they're heavy in backend processes, then you definitely need to make sure you do the object-oriented program for it as well. So that's why we were like dealing with the enterprise maybe systems. You're using the frameworks that are helping you to do like MVC, and then this whole model part has become main part that it's usually also required a lot of object-oriented knowledge and using object-oriented languages for it. So again, there's no one single solution for any problem, and we need to kind of look overall what we have, what we're going to do, what is going to be in 10 years from now, and what are the things we need to add to our softwares and our tools and our methodologies, which processes we're going to follow. And so all of those going to help us at the end to be more successful. So Lisa, I see your hand is up. Is it accidental or really have a question?
It was accidental, sorry.
No, that's okay. Okay, so I think we have all the way to 12, right? So usually you guys gonna get a break in between or not really? How that works? Did you guys get a break? I've heard that this is your third session so far. Do you have any break? Yes.
Usually, I'm pretty sure it's up to the presenter. I think in the past we've had breaks. I mean, our last one yesterday had a break, but I think it's up to the presenter.
Okay. Yeah, I think it's good to have a break for all of us, kind of see like what we deal with it so far and think about it. And then we come back again and continue. So we're going to have a maybe 15 minutes only break. So imagine this is 10:30 right now, almost. So we're gonna come back at 10:45. How about that? It sounds good to everyone?
Yep.
Okay, perfect. So see you guys then. And so I know you're recording it. Lee, are you still here? I think we're just gonna keep it. So yeah, just gonna come back at 10:45. See you guys. Bye. and also share my screen again. Okay. So we are right here. So anybody, any question before we start again? Okay, so since most of you, again, kind of already talked about these and most of you are familiar, we just kind of jump over these and just quickly kind of just review it basically. So we talk about productivity, quality, and cost and time to market. We talk about the tools and processes, methodologies. And so here we're just kind of like organize them in the based on the life cycle and all the activities that are required to be done. So, we have our entire development process. We have our QA teams. Also, there are many organizations used to be kind of breaking also the teams and organizing the teams based on that. So we have a whole team or multiple teams of development developers. And then we have our the QA team basically, and then we have our management team. So they are going to worry about all the resources, costs, making sure we get to market on time, and things associated with that, and how breaking the task to multiple teams, how to use the resources efficiently. And then also the QA would job which is to do that, mainly testing, and the development wouldn't really care that much about testing, which is following the requirement, make sure they complete their task and then pass it to QA. So this is also kind of not happening anymore that much. So this big gap between these two groups. So you see that most of the team now going to have a very good relation with the QA. Basically, we have either everybody has to do the testing. So we don't have like a developer that only do development 100%. So all the developers are in 50% of the time they do testing. So of course, you're testing for those units, individual part that you write and implement, and then maybe also some classes, but you had to do testing. So basically in industry, if you really think about it, we need more testers than developers, because again, the developers needs to do the 50% of the time they do testing, and then when we're breaking to the QA team, also they're 100% of the time they do testing. So sometimes you have some development happening in the QA part because of the new technologies. We don't really have all the tools to help us to do the testing. And so we sometimes have to implement our own tests, depends on what you're trying to do. And so it happens in that sense too, that you're implementing your own test tool. And but again, the teams are kind of working together a lot smoother when you have the developers that also thinking about testing before they're implementing. So the test-driven development is making these two teams to be more in peace. There used to be a lot of fight between these two. Also, we have now better way to communicate as far as the metrics about our QA, how we know that our software is more reliable at this point, how much test we did, how much test is enough, basically, how we're going to communicate in that sense. We didn't really have at the beginning the metrics to talk about the quality of our software that much. So it is there, and there are tools to help us to know and to kind of feel like, okay, we did test enough so we can stop, or no, we need to still to do a lot more testing. But one thing is, unfortunately, they're still never going to change, is that the fact that we cannot say when we're done with testing, we never can say that there's no fault in the program anymore. There's no basically correctness to any software. But what we do with testing is that just we're making sure that we feel more confident about what we did, and we did very systematically. We had a systematic approach. And so we feel more confident when we're done with our testing. So that's the only thing we can really do. And obviously, I guess the project management, you can imagine what they do, all the metrics they need to deal with to make sure the product was beneficial, basically, we make profit out of it in long term. And then also we have the teams that are working with each other, are going to keep them happy. So one of the job of the management is also that, in that sense, when we're dealing with agile, and many of you probably heard about agile, and one of the things is that dealing with people is not as simple as you would think. So you want them to work with each other and be happy. And so how we're going to keep them happy, keep them motivated, and all of those. So a lot of works, in all of these different categories. And, again, we may not have a complete, cutoff between, each of them. Sometimes we have teams that, 5, 6 teams, they do development. We have QA working with them, or some of them are moved between QA and developers. And then we have maybe even the leader of the projects involved. So anyway, so this is a software processes. So as you see, as we start a software, the first thing we need to know or we need to do is gathering the requirements. And that means basically talking to customers a lot. And that's a part of the job that's not mechanical. No way you can make it automated. It's the hardest part of the job. And then after we kind of get that, we have some ideas and we'll start doing some analysis. Because again, as we just talked about the farmer and the wizard example or the magician example, we want to make sure whatever statement we get from our customer, we understand that we know exactly what is the main problem we're trying to solve. So that's the goal of this analysis. And the output of our analysis is usually going to be some documentation. And it can be like we call them use case documents. There are lots of diagram in it, or domain model. So we're trying to understand what is the problem. So that's the main goal of the analysis. So here we're going to see if we miss anything, if we understand everything, and what we need to do, some kind of a way to do, or even here, maybe based on the information we get, the system architect, maybe you'll start thinking about what kind of architecture is going to be fit, what kind of software, what kind of processes, what kind of languages, like all of them is going to be, so that based on that, we're going to see also what kind of resources we need, if you need to hire more people. And then, we're focusing in the analysis today. We're going to talk about a lot of domain modeling. So we're just talking on that, which is require a lot of UML. And then we're going to design. So we're getting the output of our analysis and basically hoping that we understand what is the problem. And then now we start thinking about how and how we're going to solve it. So this is basically going to be more on the solution side. When we're doing analysis, the analysis has nothing to do with the solution. Right? The analysis is all about the problem. That's also very important. What is the problem? During the analysis, we never should think about the solution. Okay? But then when we go to design, now we know what is the problem. Now we need to think about how we're going to solve it. So what is the solution now? So the design is all about solution. So basically, sometimes we also say software as is, software to be. That's the goal. That's the solution, right? So we're going to get from here that we are right now. We want to understand exactly what we are, where we are, what we have, what is the complaint at this step that we are in it, and then where we're going to go. And so this is our job to fill this gap, right? From software as is to software to be. So basically from the problem to the solution. So the design also, at this point, we're not doing that much of coding mainly. We're focusing mainly on the design. So lots of documentation again here. And so it's going to be a lot of UML diagram, different kind. So we have a static view of our design, we have dynamic view of our design, which making sure we understand and we go through all the steps of our design. And as we do, we need to also think about the aspects of how we're going to be independent, because we're now getting ready to now start doing implementation and assigning it to different teams. So all of them happening in the design. And then when we're getting the output of our design, if we do a really good job, everything is based on UML and we do a really good job in our UML documents, then it's completely mechanical as from this step to implement codes. So implementation is the easiest part when you have your design ready. So even there are tools like plugins that your friends mentioned that they get these documents, this UML diagram, and then convert it to the code. So that part is very easy. So the main thing is you have a good understanding of what you're trying to do and then be able to do a good design. So it means that you have a knowledge of the design principles and then using the UML to draw that for you basically, right? So UML is not a technique, right? So the technique is the part that you need to know what is going to be the better way to design something, right? So those concepts that you're trying to apply to your solution to make your solution more flexible, easy to understand, easy to change, easy to test, easy to maintain, right? Those are the techniques. Then you're drawing them, it's just visualizing them, right? So making easier to, as we just mentioned, to communicate and coordinate, right? So it's always a little bit of a problem that people think that they know how to draw a diagram. That means they know how to design. They're two different things. You need to learn how to do the design. What is a good design, right? Then you visualize your design using the UML. The UML is really just a tool, right? Any question about that? Okay, perfect. So, and then of course we do testing, integration, and then go to acceptance testing. And then finally, when everything is good, we're just going to phase of the maintenance as we just talked about it, right? We're adding more things to it. So if you go through these steps, step by step, like we finish spending 3 to 4 months, just gathering requirements, no analysis whatsoever, then move to the analysis after that. It's kind of like saying, okay, requirement gathering freeze. We're not now focusing only on analysis. So we're spending another 3-4 months just doing analysis. Sometimes even these things can happen with a completely different teams because the output of that gathering is going to go to the analyzing team. So they can be a completely different group of people. They work on that, spending 3-4 months just making sure everything is good. And then their output does that go to the design. So even that can happen sometimes with a different group of people. And then they do the design, and then finally just they're handing over to the people to do the coding. So you can imagine if software is too big and we're trying to do this in this step, this manner that kind of broken from each other completely, or then it can take a year and we don't even have one single line of code still. So finally, after 3-4 months, after we get our design, we have our code and we do testing it and then something to show to our customers. So we may have a whole year and we don't even have one single line of code that is working basically, and we can show it to our customer. So in some software, it is okay, right? We don't have a customer, we don't get a feedback that much from our customer. We know exactly what we're going to do. And, it's just not that a big of a deal to just communicate with the customer that much. But again, the focus is not those types of softwares, right? We're focusing on a very specific type of softwares that they keep changing. We don't really understand what the customer needs are. Even the customer don't know what their needs are. And we're just going to keep needs to communicate. Sometimes we don't even have a real customer. Sometimes, you're trying to, build a game application and you have a targeted group of people. This group of people would like and would have interest to play this game, right? So, but still you need their feedback, because if they don't like your game, they're not going to play it, and you spend a lot of time designing and implementing it and nobody's going to play with it. So you just make sure that every time, we peel a little bit of it and show it to them, see how much they like it, and then they give you feedback. So that's what we have a lot of like free versions of, lots of different applications. So people will start working on those free versions, and if they like it, their feedbacks and, the fact that they keep downloading it and they keep using it, that's telling you that, you did a good job. So, you can move on to the next step and then add more features and things to it. So if you're doing it in this manner, which we call it waterfall, it's not going to be like, constant feedback. You can't really use that. There's no way you can do that because there's nothing to show to your customers. So you cannot show your analysis diagrams to your customer or your design diagram to your customer, and they have no idea what is going on in those diagrams, right? So there's no way you can do that. So the only way you can ask and get feedback from your customer, you have something we call it production level, some sort of code that is actually working, and then they can just start using it and give you feedback. So again, this is like a conventional old way. It's very good fit maybe for some sort of basically like, you know, functional type of application, even, you know, maybe a very good fit for the computer science type of problem, but it definitely not very good fit for the problems that require a lot of change and constant feedback in the problems. We don't really know what we want to do. Our customers don't really know what they want. And so they need and require a lot of constant feedback from our customers. So we call these types of problems the problems that are going to be a very good fit for the object-oriented. So when we're dealing with these problems and we move from conventional functional programming to the object-oriented programming, we need to also change everything, you know, as far as all the processes, methodologies, tools that we're going to use in all over, we have to change them all. So basically we have to change our view completely. So as you can see in the object-oriented, and we even call this now software engineering that is based on object-oriented. So it's object-oriented software engineering, because all the processes, all the methodologies, all the languages, even the modeling languages we're going to use is going to be there based on that, you know, based on object-oriented. So in the object-oriented, we see everything as objects. So we need to know what is an object. That's very important first thing first. And then these objects needs to communicate with each other. So we need to understand what this communication is, what kind of relation we're going to build between these objects. After we completely understand what is an object, basically, then we'll start thinking about what is going to be the good relation. And we have different kind of relation and different combination of these relations that we create between our objects is going to be called design pattern, right? So these design patterns are basically just those UML diagrams kind of telling us which kind of objects you need and what is going to be the best relation between these objects to solve these specific problems. So we have design pattern for different types of problems. So there are, how many of you heard about design pattern? Okay, good. So there are like maybe thousands of them, right, available right now. Depends on what you're trying to do again and what kind of stuff are you dealing with. But there are some core principles, I have to say, or core design patterns or design principles that are very important in object-oriented. So what we're going to do today, we're going to talk about definitely some of those very basic main principles that you have to follow. So many of you saying that we did object-oriented programming, we learned Java, we did C++, but when we really ask you to show your code or give us like what you did, we realized that you didn't really do object-oriented, right? So I have a student in my Java class that did create some classes. It feels like, you know, there are multiple classes in the project, but then when I looked at the code, everything was static. Anybody knows what the static means?
No mutation. They could exist completely separate from
Statics
the
are belong to a class, basically, right? So you don't have different instances of a class. There are no objects involved. So it's basically functional programming. When you do everything is static, you don't do any object-oriented programming because you're not even creating any object. Everything is static. So everything belongs to the class. There's no need to create any objects. So there's no instances of your class created. So, and all of these relations that we talk about it, there's no, you know, they don't really make any sense when you do everything is static. What we do sometimes need some static things, you know, some static members, but not everything is supposed to be static. So those are like some of the very basic principles of object-oriented that even though students pass the object-oriented classes, they may not still understand it fully and they just implement everything purely functional, but then since they just did using an object-oriented program, they feel like, oh yeah, I did object-oriented program, I know Java, but none of them actually try to create these objects, creating these relations, make them work together and make a very completely flexible object. So that's one problem we have, unfortunately, sometimes. So we're going to cover that. We're going to basically review everything. Like, you know, if you don't know static, non-static, you don't know what is instance, you don't know what is object. So sometimes I have a student, they don't know what is class and what is an object. What is the difference between that? We're going to talk about all of them because the reason we need to talk about all of them and review all of them is because the UML, when it's designed for object-oriented programming. So it's all about objects. It's all about the relation between these objects. If you don't have those basic knowledge, what is an object, what is a relation, what is going on there, you will not be able to even design anything. Their design doesn't make any sense, basically, right? So we're going to review all of them together, and then we're going to try to now see, okay, when we have these types of relation, we have these types of design, how we're going to visualize our design. Again, as I just said, the UML is just a tool. If you don't understand those basic principles, you cannot really draw anything, you cannot visualize anything, because whatever you draw, it should be based on some concepts. Make sense to everybody? And here we just kind of see that when we're changing, so we have we have really three different views when we do software engineering, right? Software programming. We have a procedural, like functional, basically conventional way. Everything is functions, procedures. We have a main routine, and then there are lots of subroutines that they're calling each other. And again, script languages, even in Java, you can write the code like that. Everything is static and everything is going to just calling different methods of each other, right? So that is a procedural product. Everything is function procedure. They're talking and calling each other. It is going to work. You can make it modular as possible. But since there's still everything is calling each other, so you may change something, you're going to break a lot of things, right? So changing is not going to be as easy in the procedure. Adding new features, it's not going to be as easy as what we want. In object-oriented, if you're really following this concept object-oriented completely, you can add a new feature to your software without even recompiling your code. Only thing you need to compile is this new code. All the previous code that you already have, it doesn't even need to be recompiled, right? The integration is as easy as just compiling this piece that you just created, and everything else is going to work together. But you have to have it in design. You have to think about it that way. It has to be object-oriented so you can do that. We never can do that in the procedural coding or basically programming. And then we have our object-oriented, obviously, which we see everything as objects and the relation between them. And it's very natural, actually, right? Most of us first learn how to write program using functional base. Then we're now telling you, okay, let's just now back to the reality, and then let's start thinking about objects. But if you start teaching everyone with object-oriented, it's actually make more sense because, human being, everything that we see around us is objects, and all the relations, it make more sense if you see them as an objects and then just see the relation between these objects. But again, we'll first start with function, and then now we kind of see everything as functions, and it's going to be like a little bit hard to go back a little bit and see, okay, no, it's not just everything is on functions only. These functions belong to some sort of objects, and that's the behavior of that object. So let's separate them in that sense and put them back in their own places, basically. So, that's the object-oriented, basically, seeing everything objects in their relation. And then we have a data-oriented. So anybody knows what data-oriented means? Like those two, I guess you kind of know. So what is a data-oriented?
Is it like the use of databases, like an application program queries a database? And
Database, that's it, data, right? So you have everything data, correct. So anytime that information that you have are just a data and you need to find a relation between the data, then which is what we do in the database, everything in the tables, and each table have a lot of data in it. You may put things in the file and you're reading from the file. All those files are data in it. So you're organizing things based on the relation between these data. But when we do object-oriented, this data, similar to what we just saw and talk about this functions that belong to some objects, a behavior of some objects. These data also, they're not just existing by themselves. They belong to an object. They're the state of those objects. So each object have some state and have some behavior. So those states are those data, and those behavior of those functionality that you expect to have, basically, right? Those objects have. So so that's, you can see that this can easily communicate with the other two. So being as a backend or the middle part of it, web applications completely makes sense. You're getting the data, you convert them, you do like a lot of function out there, encoding some sort of objects now. So everything becomes like an object. And then you go back again, do a lot of queries, as your friend says, to convert everything back to the data. So it's kind of like data, functional, object-oriented, functional, data. So that's this whole thing, right? But how you're going to organize them in different layers and make them communicate smoothly, many of us in every day using a lot of different applications that has this setup, but we don't even realize that we're basically using all of these, views in one application. So basically that's what I was just trying to say, that even in one single application, you may have all of these views, depending on what you're trying to do, how big is this application, and how much change you need to do in this application. So again, when you do object-oriented, doesn't mean that you're going to do everything from the very beginning. Even in your single things you want to do, you need to, getting information from your users has to be object-oriented all the way to the end. No, we're dealing with data again, and we need some functions for sure. So functional program is going to be there still, but which part needs to be the object-oriented part is going to be that core part that needs to do a lot of processes for us. It needs to be very organized, and we need to keep adding things, new features, new basically different way to doing it, new change to it as we learn more and as we get more requirement from our customers. So that is the core part that needs to be mainly more flexible, and that was we call it. Then we need to use the object oriented for it. Make sense, everybody? Any questions so far? So here are some diagrams, as you can see, for each of these basically view, depends on what kind of software, which part of software we're trying to implement. We have a different view. So if our system is based on procedures, so you're going to do the analysis also based on these procedures, and everything kind of like events, and these events are going to kind of communicate with each other somehow and calling each other, basically. And then when we're trying to do the design also, everything is going to be the these procedures, and then we have the main routine and all those subroutines, and maybe a little bit of hierarchy between them to make them more modular. But again, it's just a lot of method calls. But then when we do database, again, you see we have all these data relations or data oriented relations. So we do our data analysis based on that, and then we're drawing, or feeding them. If it's a database, then we're feeding them into our ER relational, basically a diagram that showing all the relation between these tables, and they're all storing data in it. So they're storing the student data that basically mainly have the student ID and student name. And then we have the information about the different student in a different lines, and they're separated based on a particular information that are unique to that student, usually maybe a combination of multiple of these data, right? So the student name, the ID, and maybe social security, the combination of them make it a unique or database, right? The date of birth is going to make a unique user. So each individual row in this table is going to be completely a different information about different student, for example, but they're all going to be in that table. And then if you want to make the relation between this table and the other table, you need to use one that aspect that unique in the other table. So we call it foreign keys. How many of you know about foreign keys? Go ahead. Somebody raise his hand. Go ahead.
Foreign keys are just a unique identifier that can uniquely identify another table that's on. I get to uniquely identify a tuple on another table that's a tuple on this table.
yeah, basically, like, student ID, for example, imagine that's a unique identifier for the student, but then I want to show that this student enrolled in this course, and then I have this whole course table. So course has its own unique ID, and then I add this student in as a field, as a another column, and then with that unique ID. So, and because that's belonged to the student, and now it's inside the course, so we call it a foreign key, right? It's not the unique key of the course, it's a unique key of a student, and for us to identify whose student was that. But when we're in the object oriented, if I want to associate the student with a course, I'm not going to use foreign keys, right? Because there's no foreign key in object oriented, right? Because we don't dealing with data. Data is belong to those classes, right? So if you want to make the relation between these two, you need to use what? Anybody know what is a name? If I want to associate a student to a course, we should have a student objects and course objects. How are we going to associate them with each other?
Create a new object that connects the two of them. Have like an
We call it
enrollment.
what? Association, right? So you need to associate it with each other. That means you're going to keep the reference of the other objects, because we have pointers, we have references, right? So we're creating instances. This particular instance of this user itself is an object. And then the other instance of this student also is another object. And inside it, you have a data and you have all the behavior that belong to this student. And then on the other hand, you have the class course. And the class course also has all the data belong to the course. And then you create a one instance of the course object oriented, for example. That's one single object that is going to be basically an instance of that class course. But then in this course, you want to tell me that, for example, Nicholas is assigned or registered in this course. So you're going to associate this. You mean that you're going to create a reference or hold on to reference of these objects, basically the pointer. There's something that pointing to that objects, the address of these objects you created, and assigning it to this class. So we don't dealing with data, right? Everything is objects. So you need to show the references, the associations between these classes. So that's become what you see on our first model, right? So in the model part, which is our analysis, we're just going to statically show what kind of classes we want. And we're also showing that the most important attribute of these classes. And then what is going to be the relation between these classes? And we have the different kind of relations. And this is a UML diagram, right? So UML, again, mainly focusing on object-oriented, right? So they try to show other, products using the object UML basically, but it's mainly failed, right? So UML is really going to focus, and it's designed and introduced for object-oriented view, and you need to have some object-oriented concepts in mind. So you can draw that and kind of tell us what was in your mind when you were designing this, software. So the class diagram basically that you see here, these are your classes, and then you have your basically attributes, or we call the state, or those data belong to each of these classes. So classes are basically the prototype. Yeah, you're telling me if I have a student, it's very general, like I have a student, what are the most important properties, attribute, characteristics, or states you want this student to have, right? So we know a student gonna have a name, we're going, just unique to student, right? It has to be completely unique to student. So it has a name, it has an ID, and other things, right? It's just associated with the student only. And then we have a course. The course also has its own class, very general. Any course that we think about, it's going to have a name, with probably an ID, a description, syllabus, and whatever, right? basically objective of the course, the goal, what is going to be, who's going to be the instructor, all of this. So it's going to be a very general information. And then when I create an instance of that student, like I said, Nicholas, that is going to be an object. So object is what again? And what is a class? What is an object? Anybody can repeat me what I just said?
An object is an instance of a class.
Exactly. Object is an instance of a class that, basically we're having a general idea of what the student is going to have. We're creating that class. And then when I create an instance of that class, it's a very specific student. So I can reference to it. Now I know what the student I'm talking about. Okay. So that is going to be our analysis. And then we're moving from analysis to our design. And we have two main design view. We're going to talk about that, but then we're going to draw different types of diagrams. So there are mainly, I guess, 7 types of diagram available in the UML. And we're mainly going to focus on 2 of them in this session that we have with each other. One of them is going to be our domain model, and the other one is basically class diagram, and then the other is going to be the interaction diagram, and we're specifically going to talk about the sequence diagram. So because interaction diagram, we also have 2 different kinds of interaction diagram, but we're going to see that, and that's going to be our main goal. So we're not going to do functional, we're not going to do database, we're only going to focus on the object-oriented. So it's important to review the object-oriented concept. So a quick discussion. Anybody wants to add anything based on what we just said about the benefits of the object-oriented? Do you think that when we have object-oriented, we do not need any types of other views, specifically functional view anymore? Or, what do you think? Or what you learned so far?
From what it seems, object-oriented software engineering is very geared towards utilizing this paradigm to its fullest extent, and from design to implementation to just conceptualization, all of it is in this sort of mindset of object-oriented code, and it makes it really easy to integrate in new people because there's no difference in mindset. It's a very we're doing it all this way. So if you understand it at the conceptual level, you can do many of the other parts, even if you don't have understanding of the tools yet.
Very good. And then do you think you don't need the conventional approaches anymore because you have the object-oriented?
Yeah. I think obviously that the approaches of imperative design show up in different areas. I don't think object-oriented design is perfect for every single use case, but it does work well for a majority of them, and especially in enterprise design, the large scale, it's perfect for large scale design.
Exactly. Very good. Yeah, things that we keep going to change, and we need to basically be able to apply those changes easily, right? So we can maintaining it easily. So we need to have those approaches in mind, but definitely that doesn't mean that then we don't need the other approaches. And I just kind of give you the example that, even with the enterprise system, you're going to use all of them actually, right? But the core part mainly is going to be the one that is going to be focused and use the object-oriented concepts for it, so we can make changes. So now that we have some basically motivation, like why we need that and how it is important for us, we're going to talk a little bit about the analysis. And so in the analysis, again, we may do a lot of different things as we do analysis, but the main thing we need to do, as I said, answer what is the problem, right? That's the main thing we need to do in analysis. And in order to do that, and since we know that this is a very larger scale system, and we need to model it like that, we decided that we need to understand it and do it based on object-oriented concepts, right? So that part is aside, so we don't deal with anything else. Everything is now object-oriented. Now that we know and we're convinced about it, then our first step is to start do our model, the first step, right? We call it domain model. And in order to, and domain model, again, the answer that the domain model is going to give us is what is the problem, right? We're in the problem environment. We're not in the solution environment. That's something that you always have to keep in mind when we're dealing with analysis. We're not looking at the solution yet, because we still have to make sure understanding the problem, right? So analysis is all about problem. So we are trying to, based on whatever we get from our customer, we have a meeting with them, we come back home, they give us some statements, we maybe write it down or whatever, however we're getting the information. We're going to now start looking into it, and we're trying to now understand it. But as we're trying to understand it, we also want to convert it to the object, right? So the first thing for us is to understand what is an object. What do you think? What is an object?
An object is any encapsulation of state and behavior in particular that mutates or adjusts that internal state.
Okay, yeah, so you want the objects to be complex enough to have some information, some characteristics, and some behavior. Correct. What else? How am I going to find that? Is it hard? Is it easy? Look around you. Do you see any object? I see some of you nodding. So yeah, you see a lot of objects. Can you give me some of them?
Isn't an object defined as a set of data and a set of operations that can be performed on the data?
I know, but how am I going to find that? I know definition is that, right? This is what we know as an object. But look around you in your house, in your room that you're sitting right now. Do you see any object?
Like an example could be like a water bottle. Its internal state is how much water it has. And an operation would be drinking from it.
Basically, anything around you is an object, isn't it? Any object around you is an object, right? So any noun is an object, most likely, right? So when you have this description and you're talking to the people, just any noun you see is most likely going to be an object. And how are you going to verify if this is really an object or not? We have the definition, as you all mentioned. It needs to have a state. It has to be complex enough that has a state and has some behavior. If it does have that, then it's an object, as simple as it is, right? So basically, that's what I said, that even if you understand what object-oriented is, it's actually make more sense and easier to design everything based on object-oriented, because everything we see, we're dealing with it every single day. But the problem is we first start with functional. Now we see everything, we force ourselves to see everything as functions. And then now it's hard to go back and then say, okay, no, these functions are not just by themselves. They belong to some sort of objects, right? But naturally, that's what it is, right? So you're trying to describe anything for anybody. You start describing it because they're objects. So describing some objects and how they relate to each other. That's how we're taught, like I'm trying to even describe that the student's going to register for a course. Everything I said is based on some sort of objects in the relation, right? What kind of object I said in this statement? Student's going to register in a course. Do you see any object?
Student and course.
And what is the relation between them?
A student registers for a course.
Register, right? So even it's our normal communication, without even thinking, we're talking in object-oriented, right? So it's not hard. It's just that, again, you just the mindset, go back and think about everything that is going to happening and how you're going to not draw that, right? So just same thing. Now how I'm going to draw it, because I know how to write it. I can find the objects. I can find maybe the states of it, easily. I can find maybe even some of the relations between them easily, but now how I'm going to visualize it. So now everybody else getting the same picture as I am getting, basically. Make sense? And that's how basically UML is going to help you. So just reading this again, you see that everything around you, any noun most likely that's going to happen around you, as long as those nouns are not text or just numbers, right? those are definitely going to be an object or class, basically, right? At this point, we're trying to identify the classes. So basically a prototype of them. So we have chair. And so when we're creating a class chair, we're thinking about, things that are common between all the chairs, every chair, how we're going to identify the chair, maybe the size of it, the shape of it, whatever it is, that makes it to be chair. Because chair is an object, and how we define this chair, how we know this is really a chair based on those attributes of it. That's how we know this is a chair. And then the behavior of it, like how we sit on it, how how comfortable it's going to be, right? So those are going to be some of the behavior that the chair is going to give us, right? So then we're going to think about those behavior. But mainly what we're first going to start is finding the classes, which are basically those objects that are around us and nouns, and then come up with like more general view of them, come up with what are the main most important attributes of this chair that makes this a chair. What is the most important attribute of this student that makes this a student? And what is the main attribute of this whiteboard and make it a whiteboard? And when we find those individual classes and their attributes, then now we're going to now think about how they're going to relate to each other. What is the relation between the student and the whiteboard? What is the relation between the student and the chair, right? So then you're trying to do the association between them. So any questions so far? So we learned what is an object, what is a class, how we find them, and then how maybe find some of the main attributes of our classes. So in the object-oriented, first we do analysis, and that means that we do our model. And this part, as I said, and you can kind of see here, it's completely UML. We use all of the features of a UML class diagram because we have different kind of diagram, as I said, in the UML. But for modeling part, we use all the features of most of the features of the class diagram, UML class diagram, but we're focusing only on the problem again, right? System as is, because we want to understand it. So we're finding all these classes, all these relations. Many of these relations that we may find based on the description, they may not even be helpful for us in the software, right? And many of them, we may have to adjust it. We have to maybe add a lot more classes to our design at the end. So make the software more flexible, right? Apply all those design patterns and all these principles. So the model that we're going to create in the analysis phase are going to be more conceptual model, right? Again, system as is. What is the problem? We're trying to just understand the problem. And then when we're going to our design, then that's all going to be the classes that actually going to be implemented. So they do have all of the behaviors and the relation is going to be very clear. We're maybe change a lot of things, but our starting point is going to be model that, and then we use a lot of those information in the model inside our software design, but then we improving it. We're trying to solve something now. Again, the model is for more on the problems, finding what is the problem, and that sense. And then when we're going to design, now that's our solution, right? How we're going to solve that problem. So with both of them, as you can see, they kind of look like each other, right? They kind of look like a class diagram. And yes, as I said, they both are going to use the UML class diagram, but then the emphasis, the focus are going to be different. The focus when we're doing analysis and we're drawing our diagram is on the problem. The focus is when we're doing our design and we're doing the UML class diagram is going to be the solution. Make sense? Okay, but both are UML class diagram, right? So that's what we're going to talk about, all the rules and how we're going to show classes, how we're going to show the relations, all of them. But then you need to keep that in mind that your diagrams that are come up at the output of your analysis are not going to be exactly similar to what your code is going to be, how you're going to implement things, because that's not your solution. But the output of your design, definitely is going to be very, very similar to what is the program is going to be, what you're going to be implementing basically. But both of them are using so here's just whatever I just said. So basically, you know, that's the first step, the domain modeling. And in order to do the domain modeling, we're just going to focus on the knowing some of the basic of object-oriented and just the conceptual model again. But again, we're using the UML class diagram. So here, if you click on this, I don't know if you have access to these slides already or not, but if you click on this link, we're kind of introducing the UML. But also, I have a link to their website that I said we're going to talk about. Can you see this website now? Okay, so it's basically the specification for the UML 2.5, the one that we're going to focus on all of the kind of rules based on it. So you can kind of using it as a reference, whenever you don't know what to draw something. So you see all of the different kind of diagrams available, and it's also going to show you the in this part you can see the UML, all of the UML diagrams, and we also and also the fact that it's for 2.5, and it's just also going to give you a lot of history and all of that. So I really suggest you kind of look at it and see all these type of diagrams available, and each of them are going to be helpful for something. Some of them are going to focus on the structure. So basically they're static because they're focused on the structure, and some of them are focusing on the behavior. So they're basically kind of more dynamic. So as I said, we're going to use two diagrams mainly in this class, talk about only those two. One of these are class diagram. So we see it's in the part of the, or is one, it's one kind of the structural diagram. And then another one we're going to talk about is going to be the interaction diagram. And then I specifically mentioned that in the interaction diagram type, we're only going to show you some sequence diagram, some of the rules for the sequence diagram. So only these two. And you see the sequence diagram, which is, so anybody know what this triangle pointing to this interaction diagram means? Anybody can read this basically diagram at this point without going to a lot of details? Some of you said you already have some experience in UML. Anybody can read this diagram for us? Okay, so as I said, the UML has rules. Any relation, any association that we make has a meaning. So this is called generalization, and it's mainly used for inheritance. When we use inheritance, anybody familiar with inheritance, polymorphism, those concepts? Yeah, those are very important concepts, especially when interviews. So keep that in mind. So anyway, so when you show it this way, basically it's kind of like showing you a different kind of the same thing, right? So these four are all considered as interaction diagram. They're all different kind of interaction diagram. So sequence diagram is a interaction diagram. So is a rule for the generalization. If you want to know if you identify your generalization correctly, you're going to use is a rule. You cannot just go ahead and extend from any classes, basically inherit from any classes. You only inherit from the classes that are exactly the same type as your class. Imagine you have an animal class. So cat, dog, all of them are different kind of animal. So that make very sense to inherit from animal. But imagine I have a car. Car cannot extend the animal. Does no make no sense, absolutely. When you're reading a diagram, in the UML, knowing the basic of the object-oriented, and you suddenly see that a class that is, car is inheriting from an animal, that there is something wrong, right? So that's not a design that makes sense. I mean, design needs to make sense. It should be readable. It should tell you the story and obviously, there's something wrong because car is not an animal, and that right there, you cannot read this statement anymore. That's kind of make no sense anymore. So, this design has some issues, right? So back again here, again, as I said, the sequence diagram is a type of interaction diagram. So sequence diagram is an interaction diagram, and interaction diagram, you see the relation, is a behavioral diagram. And then behavioral diagrams are part of the UML diagrams, right? So, so basically, indirectly, sequence diagrams are also a UML diagram and behavioral diagrams. And then in the other part, we're going to talk about the class diagrams, and class diagrams are structural diagrams, and structural diagrams are also the UML diagrams. So class diagrams are going to be the UML diagrams indirectly. So that's the inheritance that's happening indirectly. Any questions so far? So when we're doing our analysis, we're focusing more on the kind of structure. And then when we get to the design, now we need to know the behavior. So we're going to need more dynamic, basically. So that's why we're using the diagrams that show the interactions, and we're also showing the object creation and all of those other things that are happening during the kind of runtime, right? So when you're running your application. So, so make sure you have access to this and kind of look at it. So in the class diagram, lots of keywords we need to know, and hopefully most of these keywords for most of you are going to be review only. And for some of you, maybe it's new, but then you have a reference to it here, right here. So, and also I have some of those on this slide. And so we can see that UML again it's explained that it's a structural diagram, and we have a lot of things in it. And the main thing that you have is going to be your classes and your interfaces. So, basically your classifiers. So we're going to introduce classes and interfaces. So anybody know the difference between a class and interface?
Isn't an interface more just like a set of predefined behavior rather than something that includes state?
Yeah, so interfaces are basically, as your friend said, they're not classes. So even in Java, if you want to create interface, you need to use interface keyword. You're not using class keyword. But then, yeah, most of the time interfaces, they're only going to have, have a behavior that you know that there are certain objects. Even they may be completely different class of objects, but they all have a certain behavior. So you add that behavior inside this interface, and then all those classes implement. So another important thing is in the interfaces, everything is abstract. So you need to implement that. So anybody knows what is abstract means? Then we said a class is abstract or a method is abstract. What does that mean?
It means we've declared it, but there's no direct implementation of it. We just know it exists.
Exactly. It's just a signature of it, right? There's no implementation associated with it, because the implementation, the behavior, it depends on that class. Whoever implemented this is going to tell us exactly what is the behavior going to be, right? We don't have an implementation, but we know that if you're comparable, you have a compare to method, right? And then how we're going to compare you is you're going to implement it in your class, so we know how it's going to happen, right? So that's why we let the implementation happening whenever we know the concrete classes. So we have concrete classes, we have abstract classes or abstract methods. We have concrete method that has implementation, and we have a concrete classes, this abstract classes or method that is just the signature and there's no implementation associated with it. So who knows that how we show the abstract in the UML diagram? Anybody have any idea? If a class is abstract or a method is abstract in a diagram, how we're going to show it? And looking at this diagram, you probably can find, at least I can see one abstract class here.
Do we use like a dotted line with an arrow?
No, I'm talking about the class being abstract. That the dotted lines or those lines, all of those lines that you see here, there are relations. I'm just talking about the class and the fact that class itself be abstract? How we show that? Do you see any abstract class in this diagram?
Oh, is book an abstract class?
Book is abstract. How we know is if I don't have that right there, how you know this class is abstract?
It's missing the entity keyword, like the entity word next to it.
No, look a little bit closer. Maybe it's not very clear. What is the difference that you see here with this book here? You see any differences?
Italicized.
Italic, right? Correct. So the abstract method and abstract classes in the UML diagram, I'm going to be shown using italic keywords. So anytime you see a name of a class being italic, that class is abstract. And also looking at this diagram, do you think it's a domain model or it is a class model, or basically the one that is going to be implemented? Can you guess? What do you see in each classes? So you see the name, obviously, in all of these classes that we have. On the top part, we have a name, right? You see the name. What else you see?
We see like attributes.
We see the attributes, exactly. What else?
Inheritance, I guess generalization as it points out here.
Relations, exactly. You see the relations between these, and even sometimes you have some, relations name or verb. You know how this relation is, like a student registered course, or we have like, the account borrowed this book item, those kind of thing, right? So you kind of see the directions and the actual relation with some verb associated with it. What else do you see? Do you see any method?
No.
No method. Perfect. So because if I had a method, I should have another section here in the class. Those are classes that they are having a behavior method in them, then there are 3 sections. Here they only have 2 sections, the name and the attributes only. So this is just the domain model. And another thing you're probably going to notice here, those are stars and 1. Anybody have any idea what they mean?
Is that like how many they have? Like
exactly.
One to many.
They show how many of these, if we're creating the objects, how many of this going to be associated with how many of the others. So we call it multiplicity, and it's showing the association between them. So here, for example, telling us that in one single account only can get 12 book, right? You cannot go over it, like either no book or maximum that you can get is 12. But then here it shows the outer of the book, and then you can see that one author can have multiple different books, at least one book or more. So I have one too many, and then each book can have multiple author, right? So it's going to be also associated with many authors, and there's no maximum to it. So basically, so that's showing the relation is many to many, basically, between the author and the book. And so mainly what we see here, we see the name of the classes are names, and the names, can you tell me what is very obvious about the name of these classes?
They're all nouns.
Nouns, and they're all start with a capital letter, and they're all nouns, and they're all singular, right? So you don't see books, you don't see accounts, although I just said that we have many to many relation between some of them, but we're not going to make the classes as authors, right? So how we show multiple of the same class? Any idea? Remember any data structure that can help you?
A list.
A list, right? So if I want to show that this relations, I have a list of this one, then I'm going to create a data field of that type. And that's how you reference them. So can you find any data field of another type in any of these classes? for example. Let's just focus on the book just for a second. Do you see any data field and data type?
What title has the type string that they show there?
So exactly, there is a title, that's your attribute, that's your state. So the book has a title, and the type of this title is going to be what? String, right? So we have some primitive types in programming languages, and we have some what we call reference type, right? So if specifically we're focusing on C++ or like Java language, as some of you are familiar with, is a string is a primitive type or is a reference type? Anybody remember? No,
It
it's not
depends.
primitive.
It depends on the language, doesn't it?
As I said, only focus on C++ and Java, object-oriented languages. What do you think?
In C++, it's a array of characters.
And in Java?
Well, same thing, or it can be a reference. It can be a string buffer or a string.
Yeah, string is a it's an object, but in the background of it is using a character array, and it's basically the character itself is a primitive type. So the string is becoming the reference type in objects, because it's basically holding an address to an array of some objects, and then we can change that, and so that's basically going to be your reference type. But if I have it, for example, I have an integer somewhere here that I don't see it right now, then maybe like, for example, this ID or something, maybe I don't know, we don't have any primitive type specifically here. But again, if you know what is your language is, and when you're using them, you can easily say, it's a primitive type or it's reference type. But a string is a library type anyway. So as you see, I'm not going to, you don't see any string class here in this diagram, because it's really belong to the library. So you don't really need to add or make your design busy by adding the library objects to your design. You're not going to do that. But can you see like another object here that is actually a reference type, and it is, you see the object right here in front of you, and it's used as a reference, as a type in another object? Can you give me an example right here in this diagram?
History on account uses account state.
Exactly, right? So the account state is another class, it's an enumeration, but it's another class. And then we have a state that is going to be that type. Mainly maybe dates also is going to be a reference. So usually something is a primitive type or reference type by just looking at the type again. So how I know these are reference type again, like the account, the date, the history, the string. Is there any way to tell you? Again, naming convention should be able to help you. Any way that you can tell, you think?
Capitalization.
Capital letter, right? So if you see that the type is already a capital letter, that's another hint for you that it is going to be a reference type. So back to basically this. So this is our domain model only. And you also can see that this is domain model right on the top. It says we're using the UML class diagram, and we have our classes, we have our relations, we have our multiplicities, and some of the attributes of these classes to show and to kind of tell the story of this system based on system as is or software as is, and trying to see if whatever we understand that from the description is also matched with what the customer really explained to us, and in between we'll find a problem too. So then when we're designing, we're going to use some of these, and then we're going to try to solve the problem. So now look at this one. What do you think is this? Is it a domain model, or it's going to be actually a implementation diagram? or design diagram, basically.
Probably more a design diagram because it's a lot more fleshed out with methods and in addition.
Exactly. So it says implementation classes. You have all of your methods and you clean up all of the relations. You have a lot of libraries, maybe they use, it's kind of like an Android application. You're talking to the third party, like you're opening a camera, like, talking to hardwares, right? So lots of things happening, and it's basically all of the behaviors are also showing here. So this is going to be more like a basically implementation diagram. And there are some interesting things, if you notice that, between this one and the other one. So for example, what you see here that you do not see here, or what we saw there that we can't see it here anymore.
There's no multiplicities.
There's no multiplicity. Good observation. Perfect. And then, many of those association verbs that you saw, or here we call them like a role, whatever ordering, those are not there anymore. So you don't have multiplicity, you don't have those association verbs. We also reduce the amount of this solid line, right? We have more dotted lines in this one than in this one. Can you see that? Why do you think it is? Any idea?
Combining objects potentially.
Why we want to do that? Why we kind of get rid of some of them and make it more like dotted lines. So is there anything is telling you, any idea you have about it? We're going to talk about that. But one thing in any design is very important is what we call coupling, right? Any idea what coupling means?
Connecting two things together.
Any relation, any association, as long as you have two objects related to each other somehow, you're creating coupling. Do you think a tight couple design is good? A design that everything talking to everything else or related to everything else? Or a loose couple design is good? Which one?
Isn't it common to say high cohesion, low coupling?
Exactly, high cohesion, low coupling. Good job. So, but basically, the tight coupling design, the design that everything is tightly coupled to each other, is bad. Why? Can you give me an example of why it's bad?
It's hard to test. It's hard to add new features because you're not sure what's talking to what's interacting with what.
Exactly. If you change anything, everything else is going to change. So ripple effect, that's what we call it, is going to be huge when you make a design tightly coupled. We object-oriented, we do our best to make our design as loose coupled as possible, because you cannot just create these classes and not let them have any relation, don't talk to each other. You cannot even implement anything if you do it that way, right? But you can minimize it. How? Any idea how we can minimize it? Using the basic principle of object-oriented abstraction, encapsulation, right? So as your friend said, high cohesion, basically creating the classes that are stupid, or we call it KISS. Keep it simple and stupid. So that is going to be the main goal, and you can only achieve that if you understand the object-oriented concept very well and know that when two objects really necessary to talk to each other, and when you don't really need to directly talk and you already have the information, so you don't need to create coupling. So knowing when you need to give the information and who is going to give you information based on what you have in your classes. And those are coming from, again, most of them coming from the basic simple principles. Just focus objects, the objects are just knowing about certain things, but they know everything about that, and they don't know anything about anything else, right? So they're just focused, stupid, and they're not curious or too smart and talking to everybody. So whenever you find that, and the diagram actually going to show you, when you draw your diagrams, you may notice that there is some objects that everybody else kind of talking to them. Those are the high couple objects. That means if I change this, everything else is going to change. And that's about design. So how we're going to separate tasks to multiple different objects or classes, basically, so that one class do not have to have all those responsibilities and be able to talk to every other objects in your design. So we want to talk about that in next class. So next class, from the very beginning, we're going to just review everything about object-oriented principles, all the way from the very basics of abstraction, encapsulation. What is a static? What is the different members? What is interface? What is classes? What are different methods? When you override, what is a generalization? All of them, all the way until we get to the point that we have everything that we need to cover. And I really, really suggest, whenever you have extra time, go ahead and review all of these things. So when we're talking about them with examples, then it's a good review. And then if there is something that you previously didn't understand, or when you were reading it yourself, you didn't completely understand, then you can ask questions. So that makes it very clear for you. You know, review before you come to the class, it can get a little bit, boring at some point, because these are all connected to each other. If one part of it you don't get it, the next part it can be harder to understand. And that's something about this topic that you kind of need to have a very good fresh memory about what happened before, and then we connect things together and you go to the next step. So it is important to kind of know that. But that's why I'm not going to talk about many things right now, let you go. But the first half of the next class, or most part of the next class, we're just going to talk about all of those relations, and a little bit talking about how we're going to use them, when we're going to use them to make our design, as we just explained, low coupled as possible and as focused as possible whenever is needed, which overall is going to help us to have a better, more flexible, easy to change, easy to maintain, easy to test software. Okay, I guess the time of the class is up, right? Is it until 12, right? Okay, perfect. Thank you guys for listening. If you have any question, you can email me. I'm going to post, I think my email was at the beginning of this slide, actually, the very first page of this slide. You can email me if there is something you want me to more, emphasize more on it, or review it. Please do that. And I'm going to see you guys on Friday. Sure. Thank you, guys. Take care.
Thank you.
Thank you. Bye. So do you want me to stop the recording, or are you going to do it? Okay, I guess I'm just going to stop the recording. Bye. See you on Friday.